Hello and thank you for being here. I'm Bozzato from Fondazione Bruno Kessler and I'm here to present the paper Semantic Visual Query Answering on Heterogeneous Territorial Data, a joint work with Giulia Bruscagin, Gaetano Calabrese, Luciano Serafini and Cesare Furlanello from FBK. In this work we present the semantic-based solution we proposed for a system for the semantic integration and visual analysis of the real estate and associated attributes data. First of all, some contact information for presenters and author of this work. I'm Bozzato, a researcher from Data and Knowledge Management Research Unit of Fondazione Bruno Kessler, and this work has been realized as a collaboration between authors of the research units for Data and Knowledge Management and the unit for Predictive Models and for Biomedicine and Environment of the FBK. In particular, this work reports some of the outcomes of the GeoReporter project, developed as a collaboration with GeoPartner of Trento, for which you may find further details at these links. In the GeoReporter project, the main challenge is that local municipalities need to integrate and analyze the information coming from different sources. With the contribution of our work, we provide a response to these needs by delivering a system for semantic integration of real estate and associated attributes data, and support for semantic visual analytic and query formulation and geovisualization. In particular, we developed three main assets: an ontology for the domain of real estate and taxation, scripts for ontology population with data from different sources, and solution for the visual queries answering over the integrated knowledge base. In the following, we will give an overview of these three contributions, starting with the domain ontology development. The goal of the realization of the ontology is the formalization and schematization of the aggregated data in the GeoReporter knowledge base. In particular, we want to represent the key object types of the domain, that is, buildings, their cadastral subdivision, and associated information. With respect to the selected foreigns, the ontology is specified in web ontology language, which allows us to take advantage of the available tools for modeling and reasoning in the standard ontology language. The contents of the domain ontology can be partitioned in different domains derived from their data source. These sources of data were identified. Cadastral data contains the principal object of the domain. They represent the central object of the model. Principal objects from this data source are land and real estate units, owner subjects and their ownership relation with cadastral units. Civil registry data contain information about family units from the municipality's registry data. Main objects of the source are resident individuals and family units. Real estate attributes data contain information from the municipality about real estate attributes from the specific year, and the main objects are municipalities' taxes to be linked to the local real estate units. Finally, utility and rent contracts domain provide data about rents and utility contracts for waste collection, gas, electricity, and water, which were provided by the municipality. The main objects of interest are contracts with the related information for different utilities linked to the specific real estate units. As you can recognize from the general schema of the project ontology, the objects from different sources have been conceptually developed in submodels and then integrated in a single ontological schema. This conceptual model has been then implemented as an OWL ontology, which is publicly available and can be reached by the references in the paper. After the realization of the ontological schema, we developed a system for importing the data from different sources and integrating this information as semantic object of the knowledge base. As noted, we have data sources from different publisher, formats, and file types that need to be merged and imported in the knowledge base. On the other hand, they may also overlap on some of their represented objects. In order to manage uniformly this heterogeneous data, we developed a two-step system for the import of the data. In the first step, the input wrapper component, which is dependent from each data source, works on the format of the input files to apply data cleaning operation and to recognize relations across entities. In the second step, different update services, which are implemented as REST interfaces, allow to interact with the knowledge base in order to update the information derived from input files in terms of the structure of the ontology. The application of this system to the input data allowed us to populate the project knowledge base with the data from the test Trentino municipalities. Finally, once the semantic knowledge base was complete with the integrated data, we concentrated on methods for the visual analysis of the integrated data. Our aim is to provide a web-based instrument that can simplify the analysis of heterogeneous data through one visual interface. The visual query answering system can guide the user to explore and combine different data sources with flexibility, consistency, and intuitivity. We thus provided three components for data analysis: a smart query builder, that is a visual-based system for complex ontology query building; the logic tree, a visual representation of the query results, highlighting the relationship within the items of the knowledge base; and the hybrid 2D-3D geographical information system, which provides a visualization for the georeferenced entities that combines 2D and 3D environments. The first tool for data analysis is the Smart Query Builder component. This slide shows a screenshot of the Query Builder interface. Basically, the queries to the knowledge base are composed using the structure and relation of the ontology components so that the user can take advantage of these even without the need to know the ontology structure and a specific query language. This method allows the user to inspect the properties of the ontology object and compose complex queries that can be saved and executed over the integrated knowledge base. The result of the query, in the case of georeferenced data, are then shown as a graphical representation over a map showing a specific cadastral information. Since the cadastral information is central to the knowledge base structure, our second visualization tool, the logic tree, provides a graphical structure that highlights the association between cadastral parcel, real estate identifier, and other related data in the knowledge base. This is an example showing the representation for a specific cadastral parcel, showing its association with the real estate identifiers over the parcel and then the specific contracts and services data related to each real estate ID. Finally, to provide a graphical representation of the real estate data, we built a hybrid 2D-3D system for the analysis of the cadastral data. The hybrid visualization allows to have a more general overview of the cadastral map with a 2D overview. Then, by selecting a specific cadastral particle, the real estate can be shown as a 3D reconstruction and allowed for the detailed exploration of the structures. As a conclusion, in our work we provided three main contributions for the development of a system for integration and visual analysis of georeferenced data. We first defined the structure and modeling of the project ontology by showing how the different data sources guided the schema definition. On the basis of this model, we detailed the integration system of the platform, which allows to clean and map different data formats to the semantic-based representation of the project IB. And finally, we presented our solutions for data visualization, providing different tools for data analysis and 2D-3D map navigation. This is all from my side. Thank you for your attention and feel free to contact us for further information on this work.